Lovejoy has degrees in physics from Cambridge and McGill University. He has been a McGill professor since 1985. For 4 decades, he has developed fractal scaling ideas in the geosciences, contributing to advances in cascade processes, multifractals, anisotropic scale invariance, space-time multifractal modeling, as well as to the empirical establishment of wide-range atmospheric scaling. One consequence of the scaling is that the conventional weather-climate dichotomy must be replaced by a weather-microweather-climate trichotomy. Lovejoy has also shown how scaling can be advantageously used to make microweather prediction as well as climate predictions. In 1989, Lovejoy co-founded the Nonlinear Processes in Geophysics Scientific Division at EGU and co-founded the Nonlinear Processes in Geophysical Journal. He was president of AGU's Nonlinear Geophysics Focus Group from 2008 to 2012 and president of EGU's Nonlinear Processes in Geophysical Division from 2013 to 2016. He is an AGU fellow and a recipient of the EGU's Richardson Medal. Much of his work is reviewed in technical monograph as well as in non-specialist texts. Let's welcome our speaker.
Anyway, thank you for that extended introduction. I'd like to thank Professor Hook and Jenzing and Anthony Davis for helping organize this and inviting me. So I'm going to try and explain what this is about, but the occasion, and this is the second time I'm giving this presentation. The first time was a month ago at EGU, the Richardson Lecture, and it turns out that Richardson actually is a kind of I can't say a mentor, but he was certainly somebody important in my research over the last decades. And in particular, in the 1920s, he initiated 2 strands of atmospheric science that I want to talk about. Those are essentially deterministic and the stochastic strands. And I want to argue today, basically, that although they are apparently incompatible or contradictory, that in fact they can be reunited today with the knowledge that we have gleaned over the last decades. Okay, so what's the problem? The problem is we're trying to deal with a system, the atmosphere, that has variability over absolutely an incredible range of scales. So, for example, in space, you can say 1 millimeter to 10,000 kilometers actually might go a little below a millimeter to the dissipation scale, which might be 1/10 of a millimeter. And in this one transparency here, you can actually see a factor of 1 billion in scales, right? We have little wisps of smoke here that show structures less than a millimeter across. We have cloud pictures taken from the roof of the physics building in McGill, which might have a resolution of about 1 meter or about 10,000 meters or 10 kilometers across. And here, if we just surf on the internet, we can easily get infrared satellite pictures with maybe 1 or 2 kilometer resolutions spanning 20,000 kilometers, roughly half the circumference. So this is, of course, clouds are basically easy to see, right? Whereas as theorists, we might be much more interested in, say, the velocity field, but which is not really possible to remote sense at the moment. But you could imagine that the velocity field, the wind field, has similar structures over this range of scales. And the wind field, of course, advects the clouds, but also advects itself, and that's the nonlinear origin of our problems, or the nonlinear terms of equations. Okay, so our job is to try and understand this. So, and given that the wind field presumably has structures also over this range, that implies that if we were sitting at a point, we would expect to have about a factor of 1 billion in temporal variability. In fact, we have the dissipation timescale, which is less than milliseconds, up to much more than just the timescale that you would get from this. The lifetime of planetary structures is about 10 days. I'll come back to that later. That's a first factor of about 1 billion, but there's another factor of 1 billion in the range of scales of, say, temperature that takes us back to the age of, as long as the age of the Earth, right? So from time, we can go from milliseconds to, well, I say 500 million years. Here, that's because that's as far back as we can go with any kind of reliable paleo data, but presumably the atmosphere was evolving and changing ever since the formation of the Earth, which would be about 10 times longer than that even. So this is the Phanerozoic. This is our best paleo temperature series over that range of scales. And okay, so you can see some straight lines here. That's obviously where there's missing data, but where there is data, and there's actually about 3,000 data points that went into this, there's high variability. We have slightly better data here, but at every scale you see high variability. I'm going to skip.
Go back.
Yes.
Yeah. How do you go from this top one to this bottom one?
Oh, well, they're different benthic stacks. So, well, I don't want to spend a lot of time getting into the details, but basically they're from essentially plankton, and when they die, they fall to the bottom of the ocean, and then you get oxygen 18 anomalies basically that correlate with temperatures and in fact other things. But okay, my point here was just to show that it's quite plausible that you have this huge range of scales for temperatures. This is skipping a factor of 1 million or so. I could have shown you intermediate pictures, but I'm trying to go through this quickly at the moment. It's just to get you an idea of what our problem is, what Richardson's problem was. Let's try to apprehend this incredible range of scales. So this is actually, well, it's actually from a reanalysis, but based on real data. 138 years in Montreal after removing the annual cycle. And I skip a little bit here, so I get down to this is 16 hertz data. And what you can see is that, let's say here, you can see that if you have a fluctuation going up, it tends to be followed by one going down. You can imagine that if I average more and more of this series, I would kill the variability. Whereas down here, at these much higher resolutions, it looks more like a random walk, a kind of a wandering signal. So if I wait longer and longer, the temperature tends to be more and more different. In fact, statistically, it is not too far from a random walk. So the problem is, how can we understand this variability and ultimately model it, predict it, etc. So that's what there's two strands of atmospheric science. The question is, should we use a deterministic or a random approach, stochastic approach? And okay, so nature is just nature. It's neither deterministic nor random. A scientific theory, on the other hand, is either deterministic or stochastic, essentially depending on whether the basic variables are defined on probability spaces or not. And so, this is supposed to show the problem. So one of these three is actual real data measured from on the roof of the physics building, actually at 2 kilohertz. So it's a component of the wind field. And then we have these two, well, we have, so I've already given it away. Two of them are simulations, one deterministic and one stochastic. And so, right, this then is the real data. And the question is, what's the optimum way of trying to simulate that and understand that? Okay, so the answer given by essentially NWPs, GCMs, is that we should have a deterministic approach, and they might give you something like that. On the other hand, if we approach the problem statistically using a turbulence theory, then we might get something like that. So actually, coming back to Richardson in 1926 proposed that the Weierstrass function. This is a Weierstrass function, which was the first continuous but nowhere differentiable function, right, going back to the 19th century. Proposed that, so it's a fractal. He proposed that the wind, the trace of the wind could look like that. In fact, there's a subsection in his paper that's entitled, "Does the wind have a velocity?" Because he thought that, well, if this was the case, then the derivative, in fact, he proposed that this trace could be the trace of the position of a particle, so that the derivative would be the velocity of the particle, and therefore it would not exist if it was a Weierstrass function. In actual fact, the problem comes with the velocity field, which would not have had an acceleration, except that there's a dissipation from turbulence that kills the behavior at small scales. But okay, and this then is a multifractal simulation of this fractionally integrated flux. Okay, so which of these two approaches does the best job? That's, as scientists, what we have to find out, and we may find, and what I'll argue is that we can use both approaches depending on our applications. They're not, in fact, incompatible. Okay, so we have to think about attitudes and essentially about determinism and chance. And I'm, although the Greeks, pre-scientific era, formulated this in terms of cosmos versus chaos. Really, the first scientific ideas about this really go back to Newton and associated with Laplace, sometimes called Newtonian or Laplacian determinism. So no room for chance. And in fact, Voltaire, who was a big Newtonian promoter of Newton, said "Le hasard n'est rien." And that means chance is nothing. And what he meant by that was that chance is beneath scientific consideration because it's simply an expression of ignorance, right? Chance is subjective, so it's not even worth discussing among scientists. And of course, that attitude evolved with the development of statistical mechanics, right? Where it was most of the details about positions and velocities of particles. I have my cup of coffee. Can I drink it or will I burn myself? I just want to know the temperature. I don't care about position and velocity of all the particles inside, right? So most of those details are irrelevant, at least for many questions, such as what is the temperature of the coffee, right? So, okay, so it's the irrelevance of the details. But even that is not really very satisfactory. And it evolved really, it evolved into objective chance, right? Just a theory, perfectly objective, that has probability spaces, random variables. I call that stochastic chaos instead of deterministic chaos. And really, with the development of quantum mechanics, essentially Born's interpretation of the wave function probabilistically, and then with Kolmogorov's axiomatization of probability theory, we can have objective chance in the most fundamental theories of science, right? So basically, there should be no stigma attached to having a stochastic theory. It's not just a kind of a poor man's determinism. It's a perfectly valid theoretical framework for doing science. And the last thing, of course, that historically that comes into this is essentially the discovery of deterministic chaos by Lorentz in the 60s that kind of led to a bit of a I'd call it kind of a backlash. So people who were diehard determinists could claim that things that look stochastic are not necessarily stochastic. And that, of course, may be true, but that doesn't mean that we should necessarily use deterministic theories rather than stochastic ones. So, okay, so here's Richardson, and he's most famous, of course, for this book he published, 1922, paid for it out of his own pocket, called Weather Prediction by Numerical Process. And this is rightly heralded as the founding publication to do with numerical weather prediction, right? So he wrote down the first complete, essentially modern set of equations of the atmosphere. He developed several numerical algorithms for solving those equations. And he actually spent then, near the end of the First World War, 6 weeks with pencil and paper trying to solve the equations. He tried to predict 12-hour pressure tendency in the central grid. Spent 6 weeks. There's an interesting book by Peter Lynch who tried to estimate the time that it would really take. He estimated 6 weeks would be very, very fast for a human calculator. But anyway, Richardson claimed it took him 6 weeks. Unfortunately, as Richardson himself had recognized, he was wrong by a factor of 100. And it wasn't until the 1970s, the problem ultimately was initialization, right? And that problem wasn't really solved until the 1970s. So we didn't know why he was wrong by so much for such a long time until so long ago. But okay, so there's no question that Richardson is the father of numerical weather prediction. On the other hand, Richardson also was the initiator of the first turbulence law, called the Richardson four-thirds law of turbulent diffusion. So here's a rendition of this with some actual data. But the interesting thing is, so now he's trying to use to say that there's a kind of collective statistical behavior, many eddies, and that's responsible for the average, say, separation of two balloons, say, or particles of air. And he claimed that this law could hold from dissipation scales right up to thousands of kilometers. So that was before somebody told him the atmosphere is isotropic and has to obey either 2D or 3D isotropic turbulence. So fortunately, he didn't know about that. And so he's considered the grandfather of turbulent cascades. And yes.
Excuse me. So he obtained this figure from observations. Is that right?
Well, these are the data points. There's only about 4 or 5 data points.
Right.
Okay, so observations.
So there is it's not a theoretical derivation.
Not very theoretically.
It's a empirical.
It's semi-empirical, right?
Okay,
it turns out that, okay, so there's this K here. This is the effective viscosity function of length scale. There's this factor K here. If you could say that Kolmogorov, what he did was he essentially by dimensional analysis found that K was the epsilon, the energy rate density to the 1/3 power. So Kolmogorov, so this is essentially the same as the Kolmogorov law. Actually.
Oh,
okay.
Because another 1/3. So you add to it, it will become the 5/3.
In Fourier space, yes.
Okay.
It's essentially the same, except that you're right that Richardson, the key thing that Kolmogorov added was the dimensional analysis, which put this on a more correct.
Yeah, yes.
Okay.
But today we only remember Kolmogorov. That's how I learned about it. And we completely, I never know that Richardson did this four-thirds.
Well, it's because there was all this messing about with the mesoscale and the 2D, 3D transition, in fact.
Right.
So there was the idea of, developed the idea in the 1930s of isotropic turbulence that was developed essentially as a way of simplifying theoretically the problem. It's the simplest theoretical framework, isotropic turbulence. And people loved it so much that they wanted reality to fit into that. And so they said, okay, so since we can only have isotropic turbulence, it has to be isotropic 3D or at large scales isotropic 2D. And so they predict a big break at around 10 kilometers mesoscale, and that would be right in the middle here. So this then became frowned upon, even though lots and lots of data since him, actually much better data, support this. And in fact, I claim that he was vindicated in 2013 with modern data. And I have a question here, yes?
No, Landau said that Kolmogorov was wrong with this K identifying as a cascading epsilon, because he said there's nothing conserved, so it's not constant.
Well, okay, but it's based on a kind of quasi-conservation, right? So
it happens to be quasi-right, but at that time Landau said this is wrong. The K is not constant.
Well, okay, I mean, all right, I don't want to go into that, talk about turbulence, because Landau was, I think, mostly pointing out that there was huge intermittency, and so that to say that the energy rate density quasi-conserved, in fact, it had huge variability, and I'll come back to that, but that's essentially where multifractals ultimately come in, like cascades anyway. But, so what prevented people from saying Richardson's right was because there was this deep-seated idea that there had to be a break in the mesoscale because the atmosphere had to be isotropic, either 2D isotropic or 3D isotropic. Okay, so, all right, and I'll skip over this little poem. But Richardson basically...
Oh yes, this is famous, yes.
This is the famous poem. All right, I have to say that the big worlds have little worlds that feed on their velocity, and little worlds have smaller worlds, and so on to viscosity in the molecular sense. So, I mean, he's basically, this is the cascade idea, right? And Kolmogorov later credited, in fact, he said also Abukov, he spoke for Abukov in a paper in 1962, and he said, you know, they were both influenced by Richardson's idea of cascades. Okay, so there was a historical connection there. Okay, so what happened? So Richardson proposed these different approaches back in the 20s. Atmospheric science went on its way, but essentially with virtually no computational power for most of that time. Couldn't recruit too many people to sit down with pencil and paper to try to integrate the equations that way. So there was a kind of a pragmatic use of either statistics or determinism depending on convenient situations. But then what happened was we had two revolutions. In the 70s, we had the numerical revolution, right? The first GCM, well, we already had some barotropic weather models, but basically the numerical approaches came of age in the 70s, especially with the solution of the problem of initialization around the mid-70s. Since then, we've had ensemble forecasting, 3D, 4D VAR, which is essentially revolutionized data assimilation in the 90s. We had extensions to climate and Earth system models from roughly 2000 on, okay? So huge numerical transformation of the field. At the same time, more or less, the mid-70s, we had the nonlinear revolution. So nonlinear processes, it was mentioned, it became institutionalized at the AGU and the EGU in the 80s and 90s. I just put a few of the key things here, mostly to do with the scaling aspects that I'm interested in. But you could say that the success of the numerical revolution was we had numerical simulations imitating, to some degree, the atmosphere, whereas I would, from my jaundiced viewpoint, claim that really if we want theoretical understanding, then we need to go down this path here. But the key point is that in the last years, I think we could claim, or I am claiming, that unity can be refound. And basically, key points of that are we've essentially have confirmed that the GCMs do indeed respect the scaling laws, which are these statistical turbulence laws. We can forecast GCM control runs. That means without external forcing. We can forecast them stochastically using scaling memory of the system. I'll tell you about that later. And we can also make better climate projections of 2050 and 2100 using scaling.
But I thought it was not the scaling, but I thought it was done using ensemble. So you run it sort of by brute force. You run it 100 times, and then you compile the statistics of that.
Well, that's this route here.
Oh, okay. That's not the
that's
same.
This route here. So I'm saying that one could. Okay.
Oh, okay. You can unify this.
You can unify these
without doing it this brute force way.
Without using a brute force.
Ah, okay.
Right.
Okay.
So, who are the pioneers? Well, these are the calling the pioneers, the people that worked on turbulence laws from Richardson, more or less up to today, right? Here we have Jules Charney, quasi-geostrophic turbulence, which was essentially an extension to the atmosphere of Craigman's 2D turbulence. And of course, we have Mandelbrot, multifractals and cascades. Okay, so all of these pioneers, calling them the pioneers here, claimed that turbulence laws look something like that. Fluctuation in the quantity was proportional to the turbulence flux, possibly with some power, but then multiplied by scale with some power. And at first, the fluctuations were just considered as differences. So velocity fluctuation is just the difference in the velocity here minus the velocity there. That's your fluctuation over that separation. Right? The turbulent flux would have been, in the case of turbulent of the velocity field, it would be, say, the energy flux density, which is conserved by the nonlinear terms in your Stokes equations, for instance.
So is the turbulent flux the same as eddy flux? Eddy energy flux, rather than this the mean flow. You subtract out the mean flow and look at the eddy.
It's real. Okay, it's actually really a flux in Fourier space. If you're thinking of it as a flux, so you have a picture where you have some fluid that's could be randomly stirred.
Spectral.
So it's really a spectral. Yeah.
Okay.
And then, so then you have it, so the notion, so you had the idea of turbulent flux was being homogeneous, so this energy flux or energy rate density, as it's also called, is more or less homogeneous, although it might be quasi-Gaussian, but relatively homogeneous. And then scale, the notion of scale was isotropic, same in all directions. But the nonlinear revolution, what did that do? That generalized all of these ideas considerably. So for example, wavelets provide an entire theory about fluctuations, essentially give you a huge framework for defining fluctuations. The turbulent fluxes were realized to be essentially cascading and multifractal, so enormous intermittency, no problem, that's what you would expect. And the notion of scale is also extended to be anisotropic, notably to take into account horizontal and vertical stratification, and also its space and time. So the turbulence laws, in other words, are fundamentally still correct, but you must generalize in order for these to be realistic. Okay, so this is, this raises another question then about the variability. So I said, okay, you could have deterministic or stochastic. You have to decide which you prefer. And that is also related to this question of whether we should model the atmosphere using high-level or low-level laws. So we're used to this kind of problem, right? So here I have a kind of billiard ball picture of atoms. So if you want, you could throw in quantum mechanics to make this more realistic. But the basic point is that when we get to many, many particles, eventually we're going to be saying, okay, all we care about are, say, average behaviors. And so we could end up, if we wanted to model, say, a vortex, we could use then continuum mechanics. And of course, continuum mechanics doesn't even acknowledge the existence of molecules or atoms, right? It assumes that matter is homogeneous, or is a continuum down to infinitely small scales. And so we're used to the idea that you could use, you could either use F equals ma, or the quantum version here, statistical mechanics here, and then continuum mechanics, thermodynamics over here. So it's really, at some point you say that most of the details are simply irrelevant. Right? You have many components, but the hierarchy doesn't stop there. So that's the hierarchy we're used to, and we just stop. We do the fluid equations. But the atmosphere is not just a single vortex, and it's not even a collection of a small number of vortices. It's more like this spaghetti picture over here. It's actually called the spaghetti plate picture. So these black things are vortices. This is actually a computer simulation, but so you have to imagine even the Reynolds number 10 to the 12 roughly in the atmosphere. So nonlinear to linear terms are about a trillion ratio. So the hierarchy continues. And that's the idea here, that these are high-level laws that just take into account collectively the behavior of all of these vortices. And so, okay, so that's also asks the question then about the details, right? So the way you think about the details is totally different, depending on whether you have a higher level or a lower level approach. So the low-level approach, PCMs and WPs. Basically, the more details you take into account, better, right? You try and take everything into account if you can. On the other hand, the high-level approach says most of those details aren't really relevant. Depends on the question, of course. And that, in fact, for many purposes, we may only need the statistics. And so the practical consequence of that is, in one case, we need supercomputers, and even today, supercomputers aren't enough. We're saying that to solve the climate problem, we need to have cloud-resolving models, and maybe we'll get these computers in 2030, and then we'll take these models that model 1 kilometer the atmosphere, stuff that lives about 15 minutes, and then if we want to make a climate projection to 2050, we just average that by a factor of 1 million and get our climate projection. That's the mainstream approach at the moment. The high-level approach says, actually, if we just need statistics, then we just need laptops. So there's a big difference there. Okay, so continuing with the details, right? The usual way of looking at the details is, you zoom in. This is Leeuwenhoek. You zoom in and you discover something totally new. Every factor of 10 or so in scale gives you some new physics, in this case actually biology. You discovered microorganisms. And when you apply that to the atmosphere, you get this picture that actually comes from the NOAA Paleodata website. And they tell you this is the way you have to think about atmospheric variability. So they say, here's variability. These are the range of scales that they indicate. And these gray things are narrow range in time processes, and you have a separate theory for each one of these, basically. Okay, that's what they tell you. And then this bottom line here, this continuum background, they don't even mention it. It's not important. Don't worry about it. And they mentioned that their picture is essentially an updated version of one by Murray Mitchell. This is 1976. This is from his actual publication. Mitchell was publishing at the dawn of the paleoclimate revolution, right? He was just starting to get lots of paleo data. So he himself said this spectrum was just an educated guess. So here you have you can't really read these things. It's not important, really. This is their diurnal spike, annual spike, Milankovitch astronomical spikes, etc., right to the age of the Earth. But basically, you have a nearly flat white noise background spectrum. The only thing is, that's wrong by a rather large factor, and the rather large factor is actually 10 to the 15. Okay, so you put modern data on there, and you get something that looks, well, this is what it actually is with paleo data and real instrumental data. This is for globally average temperature. This is for regional temperature, but all this is instrumental. And then, so one thing you could say, so in other words, almost all the variability then is not from the spikes here, but from the background, which was considered not even worth discussing. And you can more or less divide this up. It's not maybe so easy to see, but in either 4 or 5 different dynamical regimes, each characterized by.
So what are the differences between the 2 red lines?
Okay, this is for the globally average temperature, and this is for 2-degree resolution temperatures. Okay, so it's a difference in spatial scale.
You mean that you look at one particular area, which
well,
is
this would be an average at 2 degrees over the Earth.
Okay.
And this is then the average of the Earth, and then you take the, so you do, okay, so one is the average of the small scales, and then the other one is the spectrum of the large scale average.
Oh, okay.
So the large scale average is going to have less variability in time, right? It's
right.
average over the whole Earth. Okay.
Right.
Okay, so what I'm saying is that you've got to turn poor old Mitchell on his head and say the background is what we should be looking at first, and the spikes are a kind of perturbation to that, right? So they, still there, there's no question. There is a diurnal cycle, there is an annual cycle, those are massive spikes, but those don't really pose fundamental problems for our science, right? I mean, everybody knows that there's a 24-hour cycle and an annual cycle. Those are important, I'm not denying it, but this is not a kind of a research frontier. Okay, so the scaling view, which was then tried to summarize in terms of those straight lines on the log-log, which are power laws, could be exemplified by, say, Mandelbrot zooming into the Mandelbrot set, and after a couple of zooms, you get something that's rather similar. Now, okay, so I'll come back to that. But, so basically, you can use scaling to classify Okay, so the problem with spectra was not that there's something wrong with spectra. There's nothing wrong with spectra, right? The only thing is, how do you interpret it? And in fact, it's so non-trivial to interpret that most publications, I could do a census, but most publications in atmospheric science where people show spectra, they don't even bother to put the units on the vertical axis, right? Because you wouldn't know, you wouldn't really know how to interpret those anyway, right? So they don't even bother. And that's why it was possible to have this astronomical error. People were looking in tiny ranges, and they didn't realize that if you actually put all the ranges together, you got this absurd result. If you thought that they were all, roughly the same level of variability. So what had to be done is we had to update fluctuations, and in fact, we did something extremely simple, which was we went back to the first fluctuation, or the first wavelet, the Haar wavelet, T10, and you say, oh gosh, I don't want to learn wavelets, that's a whole thing in itself. Well, you don't have to. A Haar fluctuation is very, very, very simple, and that's why it's such a nice thing to use. Just as if I want to know the fluctuation, the Haar fluctuation in the temperature, say it could be, okay, 2 points, I'm holding up my hand, so between my two hands, it says I take the average temperature of the left half of that interval, the average temperature of the right half of that interval, and I take the difference, and that's it. So it's the difference of averages. Combines averages, which will to do with anomalies, and gives you differences, and that's enough. So when you do that with more or less the same data I showed before, you see these regimes that have relatively straightforward interpretations, right? So this is 10 days. This is saying that it's actually RMS. So the actual typical fluctuation is plus or minus 5 degrees. So the typical difference is going to be 10. Similarly, this is for ice ages. This is from Antarctica paleo data, so plus or minus 3 or 4 degrees when you go in and out of an ice age, etc. So here I'm putting these straight lines to help your eye see these different these different regimes.
When you apply this wavelet, what does it do to periodicities? It kills them?
No. Okay, you're totally right. You must first remove the periodicities. Yes.
Oh, you remove them?
Yeah, for the daily, well, yes, the daily and the annual, yes. Because you're quite right that that's one of the huge advantages of Fourier is that it makes a nice spikes, or maybe a bunch of spikes. But yes.
But then what's the difference between Mitchell in that approach? Mitchell said,
well, the key thing was his background was flat. And I'm saying the background increases by this factor of 10 to the 15.
Okay, so, but it's still background and structures, periodicity.
Well, you can still have them, of course. But I'm saying, what is the key? Where's most of the variance coming from? And most of it is not coming from the spikes. But doesn't mean there are no spikes. Right? Okay, so the thing is that, okay, so there are a couple of key points to these transition points, the maxima and then the minima here. They should have, and they do have, very simple interpretations, right? So this is around 10 days. It actually is variable from place to place, et cetera, but it's the typical lifetime of planetary structures. Over here we have astronomical. I put plus question mark because the astronomical forcings are very, very narrow compared to what we actually see. So the astronomical forcings can only vary with great difficulty explain variability at, say, 500 years, right? Because all those forcings are 20,000 to several 100,000 years. There's many of them, but they're all at much larger scales. So this scaling regime here, not really easy to explain that way. And in here, this minimum, well, that actually depends on whether you're pre-industrial or industrial. And basically, in the industrial period, it's the time scale at which the response to anthropogenic forcings exceed the turbulent, or the natural variability, internal variability.
So this now, I've never seen this before. So you are saying, in the absence of anthropogenic forcing, this fluctuation is a minimum at this 100-year centennial time scale.
It's actually more like 500 years. This is pre-industrial, several hundred years.
Okay.
And then it increases.
Okay.
Why sometimes it's increased, sometimes it goes down, the fluctuations?
Well,
Like in micro.
okay, this has a very simple explanation. Let me just see if I can move on. Right, so what those lines, those are straight lines in log-log plot. So that means a power law. The temperature fluctuation goes as a time scale to some h. And I'm just showing here weather regime, that's less than 10 days.
Yes,
so
yes, that we understand. Yes, yes.
Climate, this is actually now using, okay, so maybe I forgot to mention, but there were three, go back to here, there are three regimes up to 100,000 years and not two, right? You've got the temperatures going up from maybe centuries or now it's decades, but up to these 100,000 year scales, and it goes down from say 10 days to time scale. So what is this saying? It's saying, you know, you average over 10 days or so, and you average more and more, and the fluctuations you get by average, you get smaller and smaller. So you think you're converging to the climate. The only thing is, after about 10 or 20 years now, the point to which you think you're converging starts to move. Why? Because of the anthropogenic temperature change. In the past, it also tended to move, but it might have only started to move at 300, 400, 500 years. Okay, but it had to start increasing again because otherwise no ice ages, right? So,
right.
So
but I can see this pre-industrial thing. Okay, what about this? You have this heavy line, the heavy line coming down, and then it hits this anthropogenic. What about this line that's above it? Yeah, this thinner line.
This is pre-industrial from the south, from Antarctica.
Oh, okay.
Okay, so this shows how, at least in Antarctica, it averaged over the last 800,000 years, but before.
Okay.
But why RMS goes down?
Because as you over this regime, it's behaving like people think the climate behaves. Like you average the weather more and more, you get the climate. That's the standard idea. And what I'm saying is, yes, the averages do go down, but then they start to go up again. And so really you have three regimes and not two. So you can call them what you like, but you don't just have weather and climate, you have a third one. And so that's where the macro weather comes in. I'm saying the middle regime here, which have the properties that we attributed to the climate, are actually,
So this empirical fact, not...
It's an empirical fact, but its explanation is not very difficult to understand, because what it means is that when you take fluctuations up to something like 10 days, you're actually, so I'm calling it a weather regime, the fluctuations are dominated by structures whose lifetime is, let's say 1 hour, the variability on 1 hour scale is dominated by structures of a certain size, maybe 50 kilometers or so.
So my concern,
and that relation goes to the planetary
if you
scale.
take turbulence, cascade always goes increase fluctuation to larger scale. So that's why I don't understand.
Oh, right. So that's this part here. Because once you get to 10 days, the lifetime of basically you're already averaging over the lifetime of a planetary-sized eddy. And so when you go beyond 10 days, you're looking at the statistics of many, many planetary structures.
So it's not.
And that's why they look at all the atmospheric fields have this feature, right? It's not just the temperature, the wind, humidity, precipitation, everything.
But it's not turbulent cascade.
So this is the largest time scale over which turbulent cascades are relevant. Why? Because it corresponds to the largest spatial scale over which they're relevant, which is the size of the Earth. So if you could have structures larger than the size of the Earth, they would live longer, and this spike would move over.
So you offer something deterministic once you reach the top of cascade.
Well, no, it could still be stochastic. Okay, I'm going to explain the stochastic models for this, but okay. And in fact, the GCMs reproduce this very well, but they are essentially stochastic over these scales. Okay, so all right. So this is just to show, okay, when H is positive, fluctuations increase. So this is actually very close to Brownian motion would have a half here instead of 4, and then this macro weather where the fluctuations decrease, of course, have a negative exponent, and here you can see the fluctuations tend to cancel each other out. Okay, so Okay, so here we have typical fluctuations go with scale to the h. When h is positive, they grow with scale. Things look unstable. When h is less than 0, they decrease with scale stable. And now we could come back to this classical idea about the climate is essentially average weather. Well, really, you should expect macro weather, right? So I think you need this intermediate regime. Climate then is the longer scale regime where things start to increase again, and people might have thinking and say that that's really what we'd be calling climate change regime, but there are 3 regimes, so you can choose your vocabulary, but there are 3 and not 2. That's the main point. Okay, so we could think about, all right, in fact, I'm going to just skip through this because I'm running out of time. So there's intermittency that we could look at, connection, okay. So if anybody's interested, I'm going to discuss all this in detail. There's a kind of a short course tomorrow morning at JPL. Okay, so I'm just going to skip through this. Okay, so why can we expect then these regimes, scaling regimes in time? It's because we have scaling in space. And so I'm going to give you a tiny little picture of that, some of the data, but really we should be concerned that in 2019, how is it that there is no consensus about the statistical properties of the atmosphere at large scale? Right? We have petabytes, probably millions of petabytes of data remotely sensed and others, and we have all these sophisticated models, and nobody seems to care about the statistical properties at lower and large scales, and they haven't bothered looking at it very much. Fortunately, we have, this is all kinds of satellite data. This is 20,000 kilometers. This is just a nice spectra, for VIS and IR and microwave and aircraft data, reanalyses. We could go on and on looking at GCM outputs, looking at NWP outputs. But basically, you get excellent scaling over the range.
So are you saying others haven't looked at those scaling laws?
Well, not in a very systematic way. So actually,
You mean papers on this are not systematic enough for you?
yes.
I can send you some we wrote.
Well,
I can send you a bunch of others.
Okay.
Some
Well,
colleagues
they are
that
not
I
okay.
wrote.
In fact, it's sufficiently confused, in my opinion, that there are papers not so ancient by people who names I will not mention, but that think that if they don't see a spectral bump in the spectrum of their model, that there's something wrong with the model.
That's not true. I mean, it's just, I don't know, if you don't want to say that everyone else is stupid, you're stupid.
I'm not saying
so.
that. I'm just saying this is a problem that has not received adequate attention. So, okay, so we went to Mars in order to be able to confirm the universality of these statistics. So there's Mars Express satellite was enough to initialize to initialize reanalyses, and we found almost identical spectra. Not only spectra, but the multifractal exponents are almost the same, etc. So in a way, this is what is expected from turbulence theory, right? When you're very far from scales that are affected by forcing or by boundary conditions, then you're expecting similar statistics. Okay, so in order for this to hold up, you can't just use the normal notion of scale. So you have to admit that scale could be an emergent property. So what does that mean? That means that you're essentially saying that the dynamics of the system tells you the correct notion of scale, and in particular, this is important for stratification. So that leads to this thing called the 23/90 model. So if you had a 2D model, which is still the reigning large-scale model of the atmosphere, you say that roughly the thickness of structures, at least over the 2D regime, is constant, and therefore the volume goes as the horizontal. I'm saying the two horizontal directions are roughly the same. Then you go as the scale squared, 2D. If you had isotropic turbulence at small scales, 3D isotropic turbulence, then you would get sort of structures would be spheres on average, and the volume would go as L cubed. And the 23/9 model, the D model, says, okay, actually the vertical is the horizontal scale to some power, and then you get So you get this L to this elliptical dimension, it's called, which is about 2.55. And okay, so it's very close to the CloudSat estimates. And the way this nice round number, 23/9, comes out is by comparing the Kolmogorov law in the horizontal, Bolgiano-Obukhov in the vertical, and it ends up being the ratio of these exponents. Okay, so that's in a nutshell then the idea that the scaling, the stratification just becomes more and more important at larger scales. So you can see, if you make a model, this would be an isotropic cross-section of the atmosphere. You zoom in, zoom in, zoom in, and you just get more and more of the same thing, right? Self-similar. But if you take the observed stratification exponent, 5/9, and you zoom in, this is a simulation, so this would be maybe a 5 kilometer across cross-section of the atmosphere. You zoom in, and as you zoom in, eventually you get to more roundish structures down here at, say, metric scales. Okay, so I will skip through this. There are implications for extreme events, spurious oscillations, tipping points, various things. Just wanted to say a few words about predictions and projections, because I promised that scaling actually serves a purpose. So I'm claiming that the study of outputs of GCMs have shown that the statistics are actually quite realistic, very close to real world. But the problem is that they're very, I mean, with a few exceptions, but the problem is they're varying around the wrong climate state. That's the main problem. So, okay, so our climate is over here. So that means that there's this possibility of using scaling models to force convergence to the real climate. So how can you do that? Okay, so we've developed this thing called StochSIPS, Stochastic Seasonal Interannual Prediction System, largely with my student Amador. And so one way of justifying this physically is to start with the energy balance equation, except you make it fractional. So the usual one is this H is 1, and you just get Newton's law of cooling. Lambda is your limit sensitivity, and then you apply it to internal variability. So these would be random Gaussian innovations, and what you find is that, okay, so you have a convolution of singularity here with a white noise, and this implies huge memory in the system, it turns out. So you get new stochastic predictability limits, and and you can check that on GCM control runs, and you can predict the GCM control runs almost to their theoretical limit, it turns out. Okay, so what happens if you use the same technology to forecast the real system, the real atmosphere? So I've got here, this is actually for globally average temperatures. So we have a skill score. It's actually the MSSS skill score for people who are knowledgeable about that. But so 1 means a perfect forecast. And what we find for this StochSIPS is some scale then getting negative, meaning it's actually ends up being a little bit, it's about the same as climatology. The 0 is climatology. The Canadian GCM CanSIPS is much worse than climatology, actually, and it's still actually considered one of the best ones in the world. Recent paper compared with others, a little bit better than persistence, but it turns out that you can use the GCM as a co-predictor, and you can do actually quite a bit better.
Predicting the seasonal cycle here?
Well, this includes the seasonal cycle that we predict, yes, and that turns out to be
correcting a model bias in the seasonal cycle effectively.
Well, okay. What we do is we remove the seasonal cycle. We remove the anthropogenic trend, CO2 and other greenhouse gases, just trying to get pure internal variability. We predict that, and then we put back our forecast of the anthropogenic part and of the annual cycle. Okay, so that's what we do. The problem exactly is for the GCMs that they can't remove the annual cycle, and that's where their source of error comes in. Okay, so
Shaun, wait a minute. Go back one. How come you don't have a perfect forecast with 0 lead time? That's not forecast.
Oh, well,
That's
okay, it's a
nowcast.
definition. No, okay, I admit it's confusing. The zero lead time means if I want to make a 1 month resolution, 0 lead time forecast, that means I forecast, take all the data up to now, and I forecast from now 1 month in the future. So they call that 0 lead time.
Oh.
I admit I was talking about a 1 month forecast horizon. That's the same as 0 lead time.
Okay.
Okay, so it's simply a definition issue. Okay, so this is what happens when you look at this in terms of the spatial variability. So you do this pixel by pixel, same procedure. Here's the CANSIP, so this is the 0 month lead. This is, okay, averaged over a 30-year. So these are hindcasts. So you can see that they do it. So red means positive scale, blue means you're not as good as climatology. So what you find is that they're not bad over the oceans, where the oceans still have in their predictability limit, and over land, negative scale. Okay, I'll be done, almost done. So stock SIPs is maybe not great, but it's better over land, and maybe a little worse over oceans, for this 1 month lead time. You put the two together in this can stock, and you get quite a lot of scale everywhere. And then this just shows the difference that we can do much better than the GCMs everywhere. Okay. So, okay, maybe just almost there. Just to show you can also project. Whoops. Okay, so you take the same equation, but you go to the long time limit, and you get a different exponent, and you can use that then to project. So here we have the gray, or the 32 CMIP5 IPCC from the AR5, the Fifth Assessment Report. You see the mean projection, and this is this huge spread. And this is for this intermediate warming scenario, RCP 4.5. So there's a huge spread. When we use this essentially system memory, we get a much narrower spread and a slightly lower value. But our projections are totally within the IPCC projection. So we have a completely new way of projecting to 2050 and 2100, and they're quite compatible with each other. So we have much greater confidence in both, in fact. Okay. How do we know that that's reasonable? Well, I can remove all the uncertainty bars, just about done now. So this is the mean of the previous one, the middle of the gray. If we take those same GCMs, we can project them using their past. And we can project them almost exactly. So the GCMs are just behaving linearly. And we can project them almost perfectly. And this then is our projection, slightly lower. And then this is a hybrid where we try to use the GCMs to help improve our projections. And it doesn't help very much. But okay, so I will just move to final conclusions. So as with any new paradigm, not only do you get new questions, but you get new answers to old questions, such as atmospheric ability, underestimated by a quadrillion. So which chaos? Well, deterministic and stochastic, depending on your application. Which level? Deterministic, or low and high, again, depending on your application. What is weather? What is climate? Well, that's clarified with the help of macroweather.
And your equation, fractal equation, describes not only weather but also in macro weather.
We have a scaling stochastic model based on the energy balance equation, fractional energy balance equation, and it allows us to make these macro weather forecasts 1 month to several years, in fact. And
just substitute negative H. What do you put into equation?
Well, we have, okay, so this is, the model becomes linear then. So we have a stochastic linear problem, not a deterministic nonlinear one. And so so that's why we need scaling operators such as fractional derivative operators. That's what we use to do the forecast and do the projections. So, all right, so I'll just, so this is the end. There's a book that just came out, which is nonspecialist, but it actually exists. I have a copy if anyone's interested. And tomorrow there is more if people want to go and talk to me. The details, so I'll stop there.
The time is up, so if you have questions.
Yeah.
Where we go from there?
That's okay, you know, I mean, it's just that I delivered this exactly,
There's a rock
exactly
okay, on
4 minutes.